Okay, hello everybody. This is Mr. Fasoni. We're going to be continuing our Chapter 9 exploration with Chapter 9.2, which is all about radians and angle measure. We already had the lecture on this about a week back, but I wanted to go over some problems from this chapter, or this section, to give people an idea on how to do these types of problems if they weren't quite catching it from the lecture, because we're so short on time. This is just an opportunity to see some more content from 9.2. So we started off with angles and standard position. That was the first concept. And just a quick review of this concept. It just means that when we have an angle centered at the origin, the initial side is always pointing to the right along the x-axis at 0 degrees, and the terminal side is pointing off in some other direction. And we measure the angle counterclockwise from what would be like 3 o'clock on an analog clock. So this example here is an angle somewhere between 90 degrees and 180 degrees because it has a terminal side in the second quadrant. Just a reminder, the quadrants are 1, 2, 3, and 4. So in class, we drew some angles in standard position. So I'll go ahead and do these very quickly, some more examples of these. And again, we're really kind of sketching these. It doesn't have to be exact, but the first one is 110 degrees. So, and actually let's use the line function. So this looks a little bit nicer. So there's my XY plane, and I want to draw a 110 degree angle in standard position. So my initial side is off pointing to the right at 0 degrees here. We know that 90 degrees is up at the top, 180 is here, 270 is there, and then we'd be back to 360 if we went all the way around the circle. So 110 is somewhere between 90 and 180, but 110 is a lot closer to 90 than it is with 180. So I'm going to say that maybe 110 looks something like this. This would be my 110 degree angle, obtuse angle closer to 90 than to 180 degrees. And then the second one is negative 900. So in class, we also talked about how angles can actually have values larger than 360 degrees, and they can even be negative. So just as a quick review on this, if I had an angle that was larger than 360 degrees, that would just mean I'd go around maybe more than once. If I went 1.5 times around, that would be a 540 degree angle, for instance. And then if I'm doing a negative angle, I just start where I normally start and I go the other direction. I go clockwise, and that would be a negative angle. The one I just drew would be negative 360 degrees. So that negative and positive idea is the same as it would be on a number line. We go to the right on the number line if we're going in a positive direction. We go to the left if we're going in a negative direction. And the number line is just the x-axis. And then, of course, the y-axis, we go up for positive, and then we go the opposite direction, which is down for negative. So in this case, I need to go 900 degrees in a negative direction. Well, remember, these would be the negative angles if I were to go around once around the circle. So negative 360 is not going to get me there. But I can just keep on doing iterations of 360 degrees to figure out how far I need to go. So this would be my first 360 degrees. I'm not there yet, so I'm going to go another 360 degrees. 2 times around would take me to negative 720 degrees. So we're getting pretty close. If I continue along, this would be negative 810 degrees. And then finally over to here at the 180 degree mark, this would be negative 900 degrees. So negative 900 degrees is really the equivalent of a straight angle, an 180 degree angle. But it's really going around 2.5 times versus just half of a time. And remember, we can find angles. Well, we'll talk about coterminal angles in a second, but this is just a coterminal angle to negative 180 or positive 180 or positive 540 or a variety of other measurements. All right, so that's sketching angles in standard position. The next thing we talked about were terminal angles, and we just kind of reviewed that up here by saying that, you know, negative 900 degrees is kind of equivalent to positive 180 degrees. We get the same angle. They're not the same angle size as far as number of rotations around, but they end up drawing the same angle on the XY plane. We'd have just a straight angle. You know, 180 degrees is this. Negative 900 degrees. Actually, let's do this backwards. Negative 900 degrees is this. And positive 180 degrees is this. They end up with the same terminal side, and that's what a coterminal angle is. Coterminal angles have the same terminal side, even though you may be going around the circle a couple different times. For instance, 500 and 140 are coterminal angles. So in class, we found a few coterminal angles, and that was just done by adding or subtracting multiples of 360, just basically adding an extra time around, whether it's in a positive or negative direction, to create positive and negative angles. So for instance, if I'm at 70 degrees, and I want to create a positive angle that is coterminal, I'm just going to add 360 degrees to 70 degrees, and that's going to give me 430 degrees. That's a coterminal positive angle. If I want to find a coterminal negative angle, I'm just going to subtract 360. What's going on here? If I could write here, I'm just going to subtract 360 degrees from 70, and that's going to give me negative 290 degrees. These are all coterminal angles. Same idea with negative 125. I'm going to add 360 degrees to it, and that's going to leave me with 235 degrees, positive. If I want another negative angle, I'm just going to subtract 360 from 125, and that's going to leave me with negative 485 degrees. So coterminal angles are also very straightforward. We're just either adding or subtracting measurements of 360 from our existing angles. All right. The next concept was radian measure. We did some drawings on this. It's kind of an odd concept, but just like on a ruler where you can measure something in inches or centimeters or millimeters or meters, you can also measure angles in a different type of measurement from degrees. And we call that measurement radian measure. What we basically are doing is taking the measure of one radius of a circle and imagining that this red line that I drew was like a piece of string that I could then drape along the outside of the circle, really, of the outside of this circle. And the distance between the start point of the angle and the end point, or the initial and terminal sides of the angle created by this radius length piece of string, we call the measurement of that angle 1 radian. And if we think about a circumference of a circle, there are going to be about 6.28, or in other words, 2 pi radian measures around a circle. I think I did like a little rainbow diagram here. This orange one would also have a radius length. This one would also have a radius length. 4, 5, and 6. This is obviously not perfect, but 6 radius lengths would get me almost all the way around the circle, and that last little bit would be like 0.28, because the distance around a circle, the circumference, is equal to 2 times pi times the radius. Well, we know the radius length, so we're going to have to use 2 pi quantity-wise of these radii to get around the circle. So we have what's called radian measure, and that basically converts from the angle measure, where we've got 0 degrees, 180 degrees, etc. We're converting to radian measure, so we have 0 radians, and over on this side, the distance that we've traveled around the circle is pi. If we come back to this point again, we've gone 2 pi radians around the circle, which is equivalent to 360 degrees. So we had some simple conversions for this. If I want to convert from degree measure to radian measure, I just multiply by this fraction, pi radians over 180 degrees. The thing I'm converting to on top, the thing I'm converting from on the bottom. And if I want to go in the opposite direction from radians to degrees, I multiply by 180 degrees over pi radians. Then we talked about this diagram. This is called the unit circle. Well, this is not really the unit circle. This is equivalent radian and degree measure. But later on in 9.4, we connected this circle and all these special degree measures to something called kind of like the labeled unit circle that has X and Y coordinates for all these points on a unit circle of radius 1. So then we converted between degrees and radians, and we'll do a couple of these really quick. So if I want to convert from 40 degrees to radians, all I have to do is multiply by what I'm going to, which is pi, over 180 degrees, which is what I'm going from, the degrees. So I'm going to show this kind of step by step, be very explicit. I've got 40 degrees times pi radians over 180 degrees. At this point, it's a matter of canceling and simplifying. The degrees cancel. That's a unit of measurement. 40 over 180, they both are multiples of 10, so I can get rid of those zeros. If I rewrite this now, I've got 4 pi over 18. Well, 4 and 18 are both divisible by 2, so I can do that, and I would end up with 2 pi over 9 radians. Very, very quick once we get the hang of it. So let's go to the next one. I'm going to zoom in a little bit because I took a little bit more room than I wanted. So if I want to do negative 260 degrees, and I want to convert it to radians, I'm going to multiply it by pi over 180 degrees. Again, I'm going to rewrite it, negative 260 degrees times pi radians all over 180 degrees. Well, now I can start simplifying a little bit. Again, I can get rid of the degree measure, and I can get rid of the 0 at the end of both of these because they are multiples of 10. Now I'm left with something a little simpler looking, negative 26 pi over 18. Again, I've got something that can be divided by 2 in both the numerator and the denominator. So I end up with negative 13 pi over 9. A lot of over 9 stuff going on here. All right, so that's degrees to radians. Radians to degrees is just the opposite or the reciprocal fraction. Pi over 9, I'm going to multiply it by what I want to go to, which in this case is degrees, over what I'm coming from, which is radians. This actually works out very nicely. I end up with pi times 180 degrees over 9 pi. Well, I've got pi in both of these, so I can get rid of those. I end up with 180 degrees over 9. And 180 is actually divisible by 9, so I end up with 20 degrees. So pi over 9 radians is 20 degrees. And now this last one, this one's actually a little tricky. It says negative 5, but notice it's not negative 5 degrees. There's no degree symbol here. So this is negative 5 radians. So I'm just going to take the number negative 5. I'm going to multiply it by 180 degrees over pi. Well, this gets kind of messy. This becomes negative 900 degrees over pi. This is actually an exact form, but if we wanted to get an approximation, what I could do is I could take negative 900 and divide it by pi on a calculator. So I'll go ahead and do that really quick. Here's my calculator, negative 900 divided by pi. It's going to give me negative 286 and then a bunch of decimals, right? So I could round this to, if I'm doing degree measure, probably 1/100 of a degree is fine. If I want to get really, really specific, I could go to 1,000th. So let's do that. Negative 286.479. I'm going to round it because the fourth decimal place is an 8. So that's going to round up to 9. So I'm going to get negative 286.479. Whoa. And to thousandth of degrees, that's pretty good unless you're doing something on a fairly massive scale, like things the size of the Earth. So we've converted negative 5 radians into degrees. All right. And then the last thing we went over in this section was arc length and the area of a sector. So arc length is basically just a portion of a circumference, and area is, or the sector area is a portion of an area of a circle. The easiest way to think about this is to think about pizza. If I've got a slice of pizza and I want to figure out how much pizza I've got, I can calculate the area of that slice of pizza. If I'm a crust person who really likes the crust, I could also figure out how much crust I have by calculating the length of the crust. Obviously, in real pizza, the crust is going to have some thickness, but maybe I just care about how much crust I have as far as distance goes. But that's a way to think about it. You're figuring out how much area you have of that slice of pizza and how much the distance around the edge of that pizza is as well. So in class, we calculated the area of a baseball field and the distance along the outfield fence as well by using arc length and sector area. So this one's a little bit of a tougher one, but I think it's an interesting one to do. This is about windshield wiper blades. So if you think about the rear windshield on a car, if you've got a, I don't know if it's a windshield on the rear window. It's kind of a weird thing. I think the windshield is technically only the front window. So the rear window, I'm gonna have to write to the people at Big Ideas Math about this. The rear window wiper of a car rotates 120 degrees as shown. And what it does is it creates like a kind of a, you know, a portion of like almost like a donut ring. If this went all the way around in a circle, we'd have something that looks like this, right? And we're only getting the area that's shaded. That circle is an empty space. So if we want to find the area cleared by this wiper, we actually have to calculate the area twice and subtract one area from the other. So in other words, I'm going to calculate the sector area for two different situations. One with a radius of 25 inches, that's the larger circle. That would be a circle created, or an arc created that looks like this. A sector created that looks like this. And then I'm also going to create a sector area based off of the smaller circle from here to there. And I can do that by calculating what's left, what this distance here is. Well, if I know the long distance is 25, then that means the short distance is going to be 25 minus 14, which is going to give me a radius of 11 inches. I'm going to calculate the larger sector area and the smaller sector area, and then subtract the smaller from the larger, and that will give me the space of the area cleared by the wiper, this weird little kind of piece of a donut. So the area of a sector, again, the equation is really easy. It's area equals 1/2 times the radius squared, we already have our radii, times theta. Well, theta is in degrees right now, so I need to calculate that in terms of radians, because when we're calculating the area of a circle or the length, the circumference around the circle, they're always in terms of pi. Pi is an integral part of that, so we need the pi measurement from a radian angle measure. Well, that's really easy to do. I want to convert 120 degrees 2 radians. I just multiply it by pi over 180. I end up getting 120 degrees pi over 180 degrees. And then I get some nice cancels. The degrees cancel out, the zeros cancel out, and I end up with 12 pi over 18. 12 and 18 are both divisible by 6, so I get 2 pi over 3, or 2/3 pi. So that's my theta. So now I just need to figure out area 1. The larger one is going to be, call it A1, equals 1/2 times my radius, which is 25 inches squared, times 2 pi over 3. We'll zoom in a little bit on this. I'm just going to bring down the half. 25 inches squared, 25 times 25 is 625. Inches squared becomes square inches, times 2 pi over 3. So this all works out to 1/2. Actually, I'm just going to make it all one big fraction. It's going to be 1 times 625 inches squared times 2 pi, all over 2 times, this is technically a 1, times 3. The ones don't do anything. Also, they technically cancel, but they don't do anything when you're multiplying, so they can go away. The 2's can also, actually, let me change from green to a different color. Let's go with pink. So the 1's don't do anything. The 2's cancel each other out. So I'm left with 625 inches squared over 3, all times pi. Let's rearrange this. This is technically correct, but it doesn't read very nicely. We always want to put our units at the end of the statement. So it's really going to be pi times 625 inches squared over 3. And then I could even move this inches squared out. So I could say pi times 625 divided by 3, or over 3 inches squared. Now, if I want to figure out this to more of an approximation, because this is hard to visualize, what I can do is I can take pi, which is just hit P on your keyboard and brings up pi, or the button is right there. Pi times 625 divided by 3 is going to be 654.498 square inches. So I can just say the approximation. I wonder why it does that every time I'm using the calculator. What was it? 654.498. 654.498 square inches. I don't know why I wrote inches to the 3rd power there, just squared. So I can get an exact value up here on the top, or if I can get an approximate value. And for real life situations, an approximate value is going to be more useful for you because you're trying to figure out real world physical quantities. But again, to 1,000th of a square inch, that's very, very precise measurements. You can probably get away with 654.5 square inches. All right, so that's area 1. Now I got to do area 2. Area 2 is just going to be the same idea. It's going to be 1/2 times 11 inches squared times 2 pi over 3. This ends up being 1/2 times 121 square inches times 2 pi over 3. And I can follow the same kind of rationale that I did before. I'm just going to make it all one big fraction because it's all being multiplied together. This is technically over 1, just in case you were a visual learner and you need to see that. So the 1's don't do anything because we're multiplying. They're just giving us the same answer back. The 2's are going to cancel. And I end up with 121 square inches times pi all over 3. I'm going to rewrite that as actually I should change the order, 121 times pi, 121 pi square inches over 3. I should have written that differently up here. It reads more nicely that way. 625 pi or 121 pi over 3 square inches. And of course, then I can move the square inches outside of the fraction. So that's the exact value. And then again, I can figure out the approximate value by just multiplying some stuff out. 121 times pi, it's going to give me 380 point blah, blah, blah. I'm going to divide that by 3, and that's going to give me 126.711 square inches. So those are my two approximate values that have been rounded to the nearest thousandth. And then if I want to figure out the area that's swept by that windshield wiper, that back window wiper, I should say, I'm just going to do a subtraction problem. And then this just becomes doing some old-fashioned subtraction here. 527.787. I should probably make sure of that with my calculator because I don't do a lot of manual subtraction like that anymore. And I'm right, 527.787 square inches. So that's the area swept or cleaned by the wiper. This little area at the bottom isn't touched because there's no wiper there. And this works on the front windshield wiper too, which is probably more something people see. I think rear windshield wipers only really are on cars that have hatchbacks. And I think even then it's not really that common. All right, so we're basically done with the 9.2 stuff. I'll go ahead and throw this on YouTube. If you have questions, please let me know. Have a good day.